So it's my great pleasure to introduce Professor Emily Tsui. Emily is an assistant professor in the Department of Chemistry and Biochemistry. Her research focuses on gaining fundamental mechanistic insight into chemical problems that challenge developing energy technology. Today, Emily will present on formation and redox chemistry of metal Polysulfanido complexes for sulfur transfer reactions. Please welcome Dr. Tsui.
Thanks. So this is the title of, I guess, the NSF award. So I'll talk basically about part of it because we've only done part of it. So thanks for having me. So half my group is interested in studying the fundamental chemistry of sulfur for kind of a number of reasons I'll get into soon. So sulfur, as many of you may know, the most common form of elemental sulfur is this S8 molecule, and that's in the sulfur zero oxidation state, so which I'll call sulfane sulfur. So it's really kind of an interesting molecule. It's like this, yellow powder. You've seen it, and I was going to show a picture of it. I didn't want to; it would be too tacky. But sulfur is most commonly a byproduct of petroleum refining. So there are like these giant mountains of it in Canada and France, and so it's kind of sitting there because we don't really know like a good way to use it. But at the same time, sulfur is really important for a lot of processes. A lot of it's converted, for example, into sulfuric acid, so sulfate, but there's also kind of a lot of current research going into using sulfur for other applications, energy applications like batteries. And you could also think about, you want to have ways to use that elemental sulfur for making new compounds, making carbon-sulfur bonds that could be biologically important. So from an energy perspective, we might be interested in sulfur in comparison to the element right above it, oxygen, because sulfur has this access to a much bigger range of oxidation states. So I mentioned sulfate, which is of course S6 plus compared to S0. And then so for this talk, I'll focus primarily on sulfur reduction. And so this is going from S0 to S2 minus, so sulfide. And so this seems relatively simple, but the issue, of course, is that sulfur really likes to form these chain structures. I don't know is there a laser pointer on this ginger?
Yeah.
Okay. Oops. Oh, that's not it. Here? That's perfect. Yes. So the reason sulfur forms this ring, for example, in the elemental sulfur form, is that it likes to form these catenated structures. So sulfur-sulfur single bonds, and then so it forms likes to bond with itself. So when you start reducing it, and then you make the sulfide can also bond with other sulfane S0 sulfurs, and then you form these polysulfide anions. So here's an example where you ring open the S8, which is neutral sulfur, and then you reduce it and you form this chain S8 2 minus anion. And so it's still forming a lot of sulfur-sulfur bonds, and this is what we're going to call a polysulfide. So the issue with polysulfides is because sulfur has formed these bonds, but they're still quite weak, so they're quite labile. So in the solution, they exchange very readily. And so even though you can get a crystal structure with S8 2 minus, in solution, it's going to exchange with a bunch of different chain lengths. So you could break apart these SS bonds. The energy is relatively weak. So you'll have a distribution of different chain lengths for the polysulfide anions. You have S8 2 minus, you could have S5 2 minus, S6. It's a whole, kind of like a giant mess. So throughout this talk, I'll refer to these polysulfide or polysulfur compounds with this SX 2 minus because we don't know how many sulfurs there are. And so this will impact our control over the reactivity. If you think about their potentials, they're going to be different in different sulfur chain lengths. If you want to think about using them to make sulfur bonds to carbon or other compounds, it's going to also be a problem. Initially, these sulfur-sulfur bonds are prone to homolysis. You break them apart one-electron processes, and you can form radicals. So here's S3 radical minus, which is also the blue color in lapis lazuli rock. So it's kind of a big problem. So questions that we're interested in looking at, from a tangentially energy perspective, would be if we want to think about using elemental sulfur, right, those big sulfur mountains, to do reactions. We want to be able to make sulfur more soluble, reactive. So elemental sulfur is really insoluble in solvents like water or even organic solvents. So if you try to dissolve sulfur in water, it's kind of float on top. It's soluble in kind of like on the order of micrograms per mil. So it's really hard to use. And so you want to be able to use that. And then the second part is, once you start breaking apart the S8 ring to form polysulfides, then how do we control that SX2- chain length in solution, and in order to control its redox properties or its behavior? And then lastly, how does having the chains compare to S2-? So I said S2-, if you add the sulfane, S0 sulfur, you form the polysulfides. How does that change the overall reactivity? How does the nucleophilicity, for example, of a sulfide compare to a polysulfide, and other similar questions. So that's what we're working on. So the chemistry of sulfur is rather simplistic from an organic chemistry perspective. So one of the most common reactions is you take a nucleophile, you can attack the sulfur, and then you do the ring opening, and you push the arrows, and you form the polysulfide chain. So here's one example by the Chen group from 2020, is if you take benzene thiolate, so thiolate is a really strong nucleophile, and then so you can ring open sulfur, and they're able to get, so again, you make a horrible distribution of different polysulfide things, right? Because again, SX2-, or in this case, this is SX- with the final group on the end. And so here they're able to get crystal structures of the 2-sulfur length. So you've added this thiolate group to one S0 atom. So this is a disulfonide. And then here, we've added the benzene thiolate group to 3 sulfur atoms, again in the S0 state, so you form what's called a tetrasulfanido anion. So we're going to call these polysulfonide anions. And again, they're going to be a distribution solution of different lengths. This nucleophile is not necessarily the easiest to work with because it is rather air sensitive. It'll oxidize in air to form other disulfide things. So another example that's really rather old chemistry is if you take a thiol, so you protonate the thiolate here, it's less nucleophilic, but still a pretty good nucleophile, and you mix it with an amine, then that activates the thiol to attack sulfur, and then go on to do further chemistry. So you form the polysulfide anion, and then that can also react with the thiol again to form H2S and this organic polysulfide compound. Sorry, the nomenclature of these sulfur compounds isn't very good, so it's rather confusing. Interrupt me if it's bad. And H2S, of course, is the gas that's responsible for the magnetic smell in natural gas. And I'm proud to say we've only evacuated the chemistry building once for a natural gas scare. Anyway, so this reaction kind of interested us, so we're trying to think about how to activate organic groups to ring open sulfur, and then because essentially what's happening here is we are taking an anionic species and then adding elemental sulfur to it, and we're solubilizing sulfur in kind of a sulfur 0 form. And then so this will be now soluble, more soluble than elemental sulfur is, and also ready for sulfur transfer reactions or other processes. So Jonathan and my group, we wanted to harness that effect of the amine on the thiol. So what he did was he took this compound, which puts an amine group right next to that thiol. And then it turns out if you add this to sulfur and benzene, then over time, within on the order of minutes, we see the formation of the expected product from the intermolecular reaction of this organic polysulfide and H2S. And we can use LCMS to identify the expected product. So here is LCMS trace of that product mixture. And we can see that we still see the thiol, this initial thiol, as well as this organic disulfide, x = 0, within this motif. And then also x = 1, x = 4 of these polysulfides, which we don't see by NMR spectroscopy here. If we look at the proton signal right next to that thiol group, we can see the thiol, the disulfide, so 2 sulfurs here, and then polysulfides. So it does react with elemental sulfur, but again, the issue is, of course, we have no control over that distribution. It's going to be a big distribution of different chain lengths. But anyway, we can monitor by NMR, and we can see over time that we can see that thiol decrease with the simultaneous rise in this disulfide, which has no elemental sulfur incorporated, and then this polysulfide, which has the sulfur incorporated into the molecule. But the point is, so we can activate the sulfur even though we don't have control. So we're still looking into this reaction. So here is again the time trace. We can see the decrease in this thiol, and then the formation of these products. But with that, we wanted to compare the effect of having this amine group right next to the thiol. Does having them together in the same molecule actually make a difference? So here, if we don't have that amine group, of course, thiols don't actually really react really readily with sulfur, so the nucleophilicity isn't very strong. or strong, not strong enough. So here is 4-methyl-thiophenol, so there's no amine group in this molecule. And then so you can see that the reaction is really, really slow on the same time scale, which 2-amino-thiophenol reacted relatively quickly. So we do need the amine group, but if we put the amine group, instead of next to the thiol, if we put it in, let's say, the 3 position or the 4 position, so here is the 4 position, so it's paired to the thiol. Here it's in the 3 position over here, so this red trace, this black trace. You can see it does react with elemental sulfur, but it's much, much slower than that original reaction with the 2-amino group. So this, I would say, would appear to be more like an intermolecular activation using the amine versus the thiol. So 2 molecules of these come together to activate the thiol for attack on sulfur. So anyway, basically we're showing here that if you have this proximal amine group, then you make your thiol more reactive, and it's still more air stable than a deep protein anionic thiolate, and then we can get sulfur to go in. And so what we decided next to do was to try this in water. So here's an example of 2-amino-thiophenol, which is, this is cysteamine, excuse me, and this is water soluble. So now we were trying to test whether this could dissolve sulfur in water. So here is just a vial with sulfur in it. You can see it's just floating on top. And so let me see if this video works. Okay, yeah, there. So Jonathan is just dropping in this amine, and he's kind of stirring it, and you can see over minutes that it's this yellow thing that's going in, it's getting darker. Oh, he just shook it. And then you can see that it gets really yellow, and all that sulfur now dissolves. And what we see is this mixture. By NMR, we can see this polysulfide compound. We can smell H2S. And then we see this yellow color, which here's the UV vis of it, that blue trace here. And this matches the formation of polysulfide dianions here, the SX2-, which again is not controlled in chain length, but does have a unique yellow signature. It's this from the literature. So that's what we're forming here. And so ultimately, what we kind of achieve by using this formulation of having an amine group next to the thiol is we can get sulfur, which I said before in water is soluble on the order of micrograms per milliliter. We can get this to be on the order of like millimolar in sulfur. So we can activate the sulfur and get it to react. And then so Jonathan's been exploring the chemistry of using these dissolved sulfur species to do sulfur transfer to compounds like olefins. So you can add sulfur to styrene, for example. But yeah, so again, the major problem still, of course, is that we haven't overcome that distribution of sulfur chain lengths, which is a difficult problem to control. So when we're thinking about this problem, we noticed that back in the 80s, or 80s, for a long time, people were using metal complexes with polysulfide anions. So again, polysulfide is all inorganic, this SX2-. But they're able to make these compounds where you have a sort of like metallo cyclopolysulfide, for example. Here's zinc, here's 6 sulfur atoms, and they form this ring. And so it's still anionic as a counterion to the zinc 2+ charge. But here, so with zinc and also with titanium, they can form really well-defined ring structures. So we control, or they're able to control how many sulfurs bind in this way. I mean, they can't predict it, but once they're able to do it, they can figure out how many there are. So this might be a way to use metals to control our sulfur chain length, and then we can control the reactivity and redox properties. But one issue, of course, is that here, if you start heating this up, you might just precipitate out zinc sulfide, a heterogeneous material. You can't really use it to keep things molecular in solution. So we turn our attention to thinking about polysulfanido complexes. So again, polysulfanidos, instead of the old inorganic polysulfide, we now have this organic group on the end here. So even though we still have a polysulfur chain, now it's monoanionic and it's bound to the metal here. And so this, by having an organic group, it's going to increase solubility and maybe also increase our cyclability if you want to think about using these species as catalysts. There are previous examples of these compounds, but they're all made through kind of harsh conditions and indirectly. So we're trying to think about ways to access these compounds using the elemental sulfur assay again. So what Moises and my group did was he took this zinc dithiolate complex. So it's again zinc with these organic ligands on it. And then if you treat this with 3 acyl equivalent of S8 in acetonitrile, so sulfur is not very soluble in acetonitrile, but if you have it in the presence of this complex, we can selectively insert 3 sulfur atoms, and you form what we're going to call this tetrasulfanido complex here. And you can see it forms this crystal structure, and then you see this, it's formed basically an 8-membered ring, zinc, sulfur, 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 carbon, carbon, nitrogen here. And this is a very selective reaction. So even in solution, all we see is one species. We have really good control over the chain length. We only ever get 3 sulfurs inserting. We never see 2 or 1 or more. So it could be controlled by kind of like the strain of the ring. But we always get 3 sulfurs, and not more or less. And we can also see this if we try taking the sulfur out, if you treat triphenylphosphate and remove sulfurs. Here's the NMR spectrum of the tetrasulfanido complex. If you remove sulfur with triphenylphosphine, we can always see is a mixture of the 3 sulfur product and the 0 sulfur product, the starting dithiolate, as we remove equivalents of sulfur. So it's in equilibrium, but we only ever see 0 or 3. So we get really good control again of that sulfur chain length. I will point out though that it is still dynamic. So if we take that tetrasulfanido complex and use 34 isotopically labeled sulfur, or isotopically enriched sulfur here, it does wash in over time, so we can see the distribution that we expect of having all 32 sulfur, all 34 sulfur, and the mixtures in between using mass spec. So here is the kind of natural abundance, mostly 32 sulfur, tetrasulfanido complex here. If we add in the elemental sulfur that's labeled, then we can see a shift to higher mass, and so that's the washing in of the isotopically enriched sulfur there. So it is still dynamic, which is what we want for sulfur, but we now get control over how many there are in the end of the speciation, which is all well and good. And then so we can also do Raman spectroscopy to look at those SS stretches. So here, the gray trace here is the tetrasulfanido. If we use our isotopically labeled sulfur, then we can shift it to lower energies and identify these different stretching modes. I don't have any comment about it, I just have this cool animation. Okay. Yeah, so, sorry, what?
It's like they're dancing.
Exactly. I think we should just admire this for another minute. Okay, I'm done. So yeah, so I guess the real question here is that high selectivity for 3 sulfur atoms. And then if we want to be able to use that to make other polysulfanido complexes, we're trying to understand, I guess, what drives this reaction. Because we looked in the literature really hard. There aren't other examples of this kind of sulfur insertion, even though metal thiolate complexes are super common. So Michael and the group made a bunch of different variations of these ligands. And then it turns out that there's actually there's different types of reactivity depending on what your ligand looks like. So here, if you take this, we had this kind of amino thiophenol-derived ligand. We had both arms before. If we make one an alkyl group, then we get sulfur insertion still. If we make both alkyl groups, we still get sulfur insertion. So that could be like a ring strain issue. We still have the same 5-membered rings here and similar geometries. But if we start changing the geometry a little bit more, if we make this, for example, here with this pyridine ethyl linker here, it's now a monoanionic complex of dianionic, but it's also a 6-membered ring here. So we've changed that strain a little bit more. So there's no reaction at all with this. So there appears to be, again, like this geometric / ring strain around the zinc that drives that sulfur insertion. Additionally, if you change it from a sulfur ligand here to this kind of analogous phenoxide ligand here, we actually get sulfur reduction. So we don't get sulfur insertion into this complex, even if there's still a zinc thiolate bond. All we see is the formation of that yellow polysulfide SX2- that I mentioned before. So there's kind of multiple modes of reactivity. It's very finicky, but we should be able to kind of design ways to control that ligand geometry to kind of select for sulfur insertion that way. Okay, but back to this tetrasulfanido complex. We're using it to do sulfur transfer to other substrates here. So if you take this tetrasulfanido complex here, add this really electron-poor alkyne, so this is dimethylacetylene dicarboxylate, then we actually see a really beautiful red color grow over time. So here, the black trace is starting material, you form an intermediate upon adding the alkyne, and then it slowly grows and has this beautiful red color. And this red color corresponds to this zinc dithiolene complex, which I've drawn the chemical over here. So what it does is this triple bond has added 2 sulfurs, and now it's an anionic ligand here. And then that has pulled away the zinc, and then so now we have a crazy octahedral zinc complex, but also a zinc bound by 2 ligands formed from this sulfur transferred product. So we can do sulfur transfer from the tetrasulfanido complex. If you do just elemental sulfur, with that it doesn't go. So basically we've activated the sulfur to do reaction, which is what we wanted. Okay, so but moving on beyond sulfur transfer, we were trying to think about the role of how that tetrasulfanido complex should compare to the starting thiolate, right? How sulfur 0 controls the reactivity of, I guess, different species. So one reaction we want to look at to compare this is this thiol disulfide exchange. So this is not with any polysulfanides. This is just a general reaction. This is really important in biology. So in biology, you have cysteines and disulfides, and they all have to be able to exchange in order to control structure and the reactive properties, like within your body or within other aspects of biological processes. So this has been studied for a long time. If you take organic disulfide compounds, so these are reduced, or these are kind of, I guess, overall typical like S+ oxidation state, if we're kind of counting electrons here. If you take a thiol, it will, over time, scramble. So here's my blue disulfide, here's a red thiol. We can form the heterodisulfide here. And so this is a reaction that's mediated by deprotonation of this thiol to get, again, higher nucleophilic attack. So if we want to compare the nucleophilicity of our zinc complexes here, I have the zinc thiolate here with no extra sulfurs, and I have the zinc tetrasulfanido with 3 extra sulfurs here. We can use these as nucleophilic catalysts to facilitate disulfide scrambling. So if you take a mixture of benzyl disulfide and butyl disulfide in DMSO, without a catalyst, they don't scramble at all. All you see are the homo disulfides. If we add in 10% of a nucleophile, in this case these are our 2 nucleophiles, we can then attack that disulfide bond, break it apart, and then result in scrambling to form the heterodisulfide. So we try to compare these two, because they both should be nucleophilic. We have a nucleophile here, and a nucleophile here. So it turns out that they both facilitate scrambling of the organic disulfide, but one takes 5 minutes and one takes 2 hours. So at a first glance, it appears that this zinc dithiolate without the extra sulfurs is, I guess, a better catalyst, a better nucleophile than this one. So it seems that the extra sulfur zeros are attenuating the reactivity of this thiolate group. So we want to look at that mechanism of how that scrambling is occurring. So we tried to take the dithiolate and add that disulfide, and then presumably if it is going through nucleophilic activation of the disulfide, we have to go through this kind of intermediate, and this releases thiolate that then results in the scrambling. So, but if you try to add even huge excesses of organic disulfides to the dithiolate complex, we never see this proposed intermediate, even though it must be there. So, we can add in 100 equivalents, we don't see anything. All we see is the starting material by NMR spectroscopy. But we're thinking that this is so this must be an equilibrium process, but the equilibrium lies heavily to the left here. So if we could think about ways to trap this thiolate, then we could drive the equilibrium forward and we can observe this intermediate here. So what we did was, you take this zinc dithiolate, you again add excess of organic disulfide, and now we can add a borane, a Lewis acid, or you can even add the carbon disulfide, for example. And that reacts with this side product, this thiolate group, and then that should trap it in the form of tetrahedral boron. And then now we can observe a new species by NMR, which we assign as this disulfide intermediate. And so it's still in equilibrium, so we still see a mixture of these 2 products, or I guess the starting material and the product, but now we can at least observe it. And we can also compare them independently. If you take the zinc dithiolate complex and add a sulfenolating reagent, so this is RS+, that should selectively sulfenolate this thiolate group, and we can access this. So we can see that also. So basically we've shown that this disulfide exchange does go through nucleophilic attack on the disulfide to form that intermediate, this intermediate, and then that's what proceeds further. Okay, but back to the comparison between the thiolate and the tetrasulfanido. I'll skip this. What we see is if you take the tetrasulfanido and you add an organic disulfide here, we actually see a lot of this intermediate here. So that was the intermediate from the dithiolate addition. So we can see kind of 2 products. This is the starting material here. This is the starting material. This is the product. Okay, they're reversed. This is the product. This is the starting material. And if you add in more disulfide, then you can drive the reaction forward to form more of this. So it appears on tetrasulfanido, we can see more of the intermediate. which is kind of counterintuitive, even though we were saying that it should be less nucleophilic. So what we're actually seeing is that we must be forming a byproduct that's more stable to drive that equilibrium. And so what we think is happening here is that the balanced reaction of the tetrasulfanido with an organic disulfide forms this disulfide exchange intermediate, followed by an aryl polysulfonide anion, similar to what I showed on kind of in the early beginning of the talk. And we can do this with different aryl disulfides. We do different substituents. You can have electron poor, CF3 chloride, electron rich, methoxyuramine. We can see different, so here's the NMR spectrum. Here's the starting material, the tetrasulfanido, and then we'll see populations of the corresponding disulfide exchange intermediate here. And it increases as you get more electron poor. So if we plot those equilibrium constants versus the Hammett parameter, which is kind of the measure of the electron richness of the aryl group, then we can see that with more electron poor, you get a higher equilibrium constant, which is consistent with our assignment here, because if you have the electron poor aryl group here, that stabilizes a negative charge, it should make a more stable polysulfonide anion. And we also observed by UV vis, so if you, again, look at this reaction where you take the tetrasulfanido with an aryl disulfide, and we can form this intermediate with the aryl polysulfonide anion, we can see the growth of a feature around 500 nanometers in the UV vis spectrum, which we assign as this species here. And again, that feature shifts in energy depending on how electron withdrawn your group is. So here again, that should change the energies of those transitions. So the conclusion here is that by having these red sulfurs here, the sulfane S0 sulfur, we can trap the free thiolate in a similar way to that we do with the boranes, and that could then drive the reaction forward. So this product is less nucleophilic than the aryl thiolate. So by adding excess sulfur, we're decreasing reactivity. So this is all fairly consistent. Sulfur 0 makes things less nucleophilic, which is great. So this this maybe seems kind of pointless, but I think having the role of sulfur in biology and in the thiolate chemistry I was talking about before is kind of an unknown aspect. So this is a pretty important kind of step forward in understanding how sulfur behaves in biology. Okay, and then lastly, we're able to use this reaction, the tetrasulfanido complex, and then we can add in sulfur to organic disulfide compounds. We take dibenzyl disulfide, the tetrasulfanido, we can start making polysulfides by NMR. We can make it. It's again, this problem is here. We have no control over the distribution. I'm drawing a trisulfide, but then over a catalytic, we can form trisulfide and then higher order polysulfides. So again, we're back to the problem of controlling sulfur chain lengths once we're away from the metal. So it's kind of two competing aspects that we have to deal with. So we're still working in that area. Okay, so with that, I think I'm out of time. I mentioned the students who are doing those specific projects in the slides, but the work is done by Moise Ballesteros, Michael Sa, and Jonathan Stoffel. And then thank you to Alan for crystallography, and FCF, my Anna Master, and Mass Spec. And thanks for your time. Happy to take any questions. Oh, yes.
So is it desirable to have, when you're doing these kind of sulfur atom transfers, do you in the end want to target kind of selectively starting one sulfur or two at a time or three? Is there sort of like a target of, two would be better because then we complete that disulfide bond, or like what is the kind of like goal of kind of selectivity in inserting sulfur?
I think it depends on what you want to do. So for a lot of compounds in, I guess, biological systems, one sulfur is maybe what you want for, I guess, some heterocycles. There are examples of trying to target two. So yeah, it depends on what you're going for, right? So it's a non-answer, but it's true.
Okay, so is this sort of like in the context of like pharmaceuticals, or what would sort of be kind of a potential target of like we would like to insert sulfur to make these types of compounds? Like is there a class or a family that would be sort of the eventual goal is like this type of compound?
I think that, well, so we haven't gotten there yet. I don't want to be an organic chemist, so I don't want to go into the pharmaceutical land. But one thing that we have been interested in recently is kind of inverse vulcanized polymers. I guess you're from Arizona, so you know. But yeah, so like sulfur, again, is that forms like from the polymers. People have been using it recently to, yeah, again, incorporate that. If you if you copolymerize it with styrene, for example, you can make these really cool materials. So again, that's a huge distribution. So if we can control the chain, we're trying to go in. does, well, so it depends on how much you add in, so it sort of reaches equilibrium, yeah. So you can drive it one way or the other, but once it reaches that steady state, it usually stays the same unless you do something to it.
All right, let's thank our speaker again.